Hello, hello. Yeah. So we were on a bit of a compressed schedule with that, and now it's, I think, going to be a little bit easier, and it'll also give you a little more time to assimilate some of the course material for the midterm number 2. So that'll be due in class, so at 11 a.m. On next Tuesday. We'll have a talc the Monday before, so the night before it's due, we'll have a talc. So you'll have a normal talc time. This will be a longer problem set. So, sort of try to budget a bit more time on this. A large part, I think, of the mathematics of what you're going to wind up seeing on the midterm will be focused on some of the things that we're doing now, this week and next week. So it'll be a good place for you to get a sense of the kinds of things we'll be looking for on the midterm. Midterm review will be that night, and that'll be in the normal talc time. So that's actually also semi-good that we don't have to schedule a special review because we already know that most of you can come to talc. Exam next Thursday. It's going to be largely the same format as you saw on the first midterm, and you'll be able to use your other side of your 8.5 by 11 cheat sheet that you used last time, calculators, pens, pencils, etc., covering everything up to class on Tuesday, next Tuesday, a week from today. My office hours, 3:30 today in Campbell 527. As posted on the wiki, finish the reading chapter 24 and start into 25.1. By the end, basically, we'll start talking about 25.1 stuff on Thursday and get into that in earnest next Tuesday. Any questions about logistics? I'm not walking out of the room. Bye. There was a question about the special review section by talc next Monday. How do people feel about 5 to 7? IDL decal aside? Is that a significant problem for people? Okay. All right. So we'll nominally say 5 to 7, and if somebody could talk to the IDL decal people and let them know that we're pulling rank and telling them that you guys should go to that. But you don't have to, of course. Any other questions about logistics? Were you guys really bummed out about problem set number 6 not showing up? Yeah.
Is there going to be a review sheet?
Yeah, we'll hand out the equation sheet that we will give you on the midterm, and we'll also post some questions, like last time. Yep. Largely, no. So unlike the final, which is sort of a cumulative midterm of the whole class, so we call it a final, this midterm will really focus on just what we've done since the last midterm. And then in the final, we ask you also, sort of pull things all together. In general, we won't kind of, balkanize things into midterms, so a given question won't be just about the first, the first sort of third of the class. It might be actually combining concepts across the whole class in a given question. Yes?
That's for the final?
That's for the final.
Okay, but not for the
Midterm, it's going to be, tell us about rotation curves or dark matter. Yeah, which you don't know about yet. Ha ha. Any other questions on logistics? Okay, so last time we talked about statistical or kinematic parallax as a way of making measurements of distance. And remember, the geometric way of making parallax to an individual object starts to break down because you have to make a very, very precise measurement of that object's position as a function of time over the course of a year. That breaks down at sort of the 100 parsec or maybe kiloparsec level. But statistical parallax or kinematic parallax, where you take a whole grouping of stars that you believe to be gravitational bound to each other, and you look at their proper motion, which is an easier number to derive from observations because you're just looking at how things appear to be moving on the sky. And there you have not to get very precise measurements over the course of a year, but instead you can get very precise measurements or even quasi-precise measurements over the course of a decade or even a century by looking at historical images of that part of the sky and looking at how all those stars are moving. And you use basically a statistical formulation to figure out what the distance is. You'll get some practice on that in your upcoming problem set. Beyond sort of a statistical parallax volume, if you want to think about distances, we need to start using bright objects. that pulsate, and the pulsational period, as it turns out, of Cepheids and our Lyrae are actually a way of us inferring what the intrinsic luminosity is. So if we can measure the period of a source which is varying, and we can associate that source with belonging to a certain class, then we can know its intrinsic luminosity, and modulo sort of dust effects, we can actually figure out what the distance is to that object, just through one over r squared law. So that pushes us out to the far reaches of the Milky Way, and then even lets us start measuring distances to nearby galaxies. We'll talk about some of the physics of pulsation when we talk about how we know the overall size structure of the universe, but the conception I think that you should have already in your minds is how we sort of build up a very precise understanding of the distances to things. You know, we have a very precise measure of the distance between here and San Francisco, and a very, very precise measure of the distance between us and the moon, between us and the sun. Size structures in the solar systems are measured very well at the sort of centimeter or meter level. And then as you go to larger and larger distances, it becomes harder and harder. But parallax is the gold standard for doing geometric distances nearby, and then you have to start resorting to more sort of statistical techniques as you go farther and farther out. But understanding the size of the universe, and now we construe the universe as things around you just in your everyday life, out to the sort of size of the solar system and beyond, understanding all of that is absolutely critical for us understanding how big the observable universe is on the largest scales. So little changes in our understanding of, say, the distance to a nearby Cepheid variable actually has fundamental consequences for our understanding of the size and even the age of the universe. So that's something we'll see a bit more of after the midterm, and we'll get into some of the physics behind pulsating variables, just as a way of us introducing how we make measurements on large scales. But we used these and talked about the size structure of the Milky Way. Our distance from the sun to the galactic center is about what? 8 kiloparsecs, right? And we're moving around the sun at sort of what speed? Or around the center of the galaxy?
233?
Yeah, it depends on who you ask, like 225. I think your book uses 225, is that right? For the rotation speed of the sun around the center of the galaxy. And this brought us into this whole sense of the great debate, which was in 1920, of what is the size structure of the then known universe, which was just the Milky Way, and what were those other little nebulae. We know, of course, that those little nebulae, or many of them, were other galaxies, much like our own, but at the time that wasn't known. And the big breakthrough there came in Hubble's discovery of pulsational variables in other galaxies, in particular in Andromeda, that allowed him to determine that this thing was very, very far away and well outside of the known size of the Milky Way. We ended with sort of a statement about the overall distribution of stars in the Milky Way, and we talked about there being some sort of exponential fall off. As you go to large radii, you wind up seeing less and less stars, and that falls off exponentially, and there's a scale associated with that exponential drop off. And then there's also two different scales as we think about the distribution of stars above and below the disk of the Milky Way, or the plane of the Milky Way. And that also, so that drops off exponentially, but it drops off exponentially sort of in two ways. There's sort of two different characteristic heights. And one is the thin disk and one is the thick disk. And they have slightly different populations. And when we start talking about the assembly of galaxies, understanding the thick disk, thin disk, and actually what we call the halo of stars around the Milky Way, it all sort of starts to come together of how we built up the Milky Way, right? It didn't just sort of collapse from nothing and this is the structure we have. The Milky Way has been built up over billions of years. And so we'll start to understand a bit more of the relationship of thin disk, thick disk, and halo stars. And I think I ended last time with a statement that the mass in the Milky Way of stars and gas and all the stuff associated with baryons, like protons, is 9 times 10 to the 10 solar masses, 90 billion solar masses. And usually this is invisible stuff, not invisible, but in space visible stuff. And this is a number that's not an easy number to derive. This is partly counting stars. This is partly sort of coming up with an overall model for the Milky Way and the distribution of stars within the Milky Way. But of course, while it may be very easy to see a big, bright blue star on the other side of the galaxy if it's a little bit off the plane, because indeed it's so bright, so we can see it. There are many of stars, as we talked about also last time, that may be incredibly red and incredibly faint and yet be nearby. So this is sort of also doing the statistics and the demographics on the stars that we don't see, using the stars that we do as sort of a proxy for that. The Milky Way, mass of the Milky Way in the dark stuff, the stuff that we don't see and can infer, say through 21 centimeter observations or carbon monoxide observations, is, just to give you the number, 2 times 10 to the 11 solar masses in what we call dark matter. So this means that of order 75% of the matter in the Milky Way is unaccounted for by normal astronomical means. No one's freaking out? You're all okay with this? Man, every year someone gets up and they pull their hair out and they run out and never see them again. But you guys are stronger than that. So the subject of today's class is us coming to an understanding of how we actually make this measurement if we're talking about figuring out what's there that we can't actually see. Okay, so that's one of the big subjects of today. And then what we'll start on is a discussion of how we can use the stuff that we do see to try to infer just what this dark matter stuff actually is. And dark matter is an issue that sort of rears its ugly head on all different scales that are important to us astrophysically. The Milky Way is the most obvious one, but dark matter is also manifest on the largest scales as well. And the presence of dark matter is actually quite important for the formation of structure in the early universe. So it may just sort of seem like a bit of an annoyance here to try to figure out maybe it's just some sort of weird little particle or maybe some super red stars that we haven't even seen that may actually be there. That kind of stuff we can actually start putting constraints on observationally. But we really have to understand what dark matter is because it may actually give us a real big clue into the physical universe that we can't actually measure and don't have access to in the laboratory. So the way in we make measurements of mass interior to a certain orbit is just use satellites around that central mass. We can make a very precise measurement of the mass of the sun by looking at the period and the various orbits of each one of the planets. And there's a rotation curve associated with measurements of the solar system, and likewise, there's a rotation curve that's associated with the Milky Way. So this is just a statement that the velocity at some radius from a central mass depends on the mass interior to this distance r. Looking down on the Milky Way, here's our spiral arms. If we make a measurement of some object moving around, now we'll just assume a circular orbit around, it will have some velocity, it will have some distance from that center, and in a sort of purely Newtonian sense, we can say that the centripetal acceleration of the motion in the circular orbit is going to wind up being balanced by the force that this particle is feeling inside. So F is just gm of the galaxy interior to this radius, so less than r, times m of whatever the particle is of interest, divided by r squared. This is just m, little m of the particle of interest, v squared divided by r. Cross these out, and we see that the mass interior of the galaxy less than r is just v squared r divided by g. We can put in the numbers for what we have at a radius of the sun around the center of the galaxy, and given this velocity here, we can parameterize this as 8.95 times 10 to the 10 solar masses r divided by 8 kiloparsecs, v divided by 220 kilometers a second. Right, in detail, you'd actually have to make a measurement of v as a function of radius and figure out what the densities are at every single radius. But this is a way of making just sort of a quick and dirty measurement of that internal mass. Right, so this, by the way, is more basically a statement interior to the radius of the sun around the center of the galaxy. So if the rotation or the circular velocity of the sun around the galaxy were higher, or we someday realize that our observations were wrong and it was a factor of 10% higher, what would that do to the mass, the effective mass of the galaxy? If I raise this by 10%, this number is going to go up by 20% or something like that, right? Likewise, if it turns out that we look at our circular velocity around the galaxy and it turns out to be much lower, the overall mass that we infer is lower. And likewise, if we're at a different radius, we can raise or lower the mass by a certain amount, proportional to the change of that radius. So this is interesting in, I think, a fairly deep way in that it allows us to make a measurement of the mass interior to the motion of the sun around the galaxy in a way that's completely irrespective of our individual measurements of counting stars or looking at 21 centimeter gas blobs, right? This is a purely dynamical measure of the mass of the Milky Way. And likewise, doing this with the virial theorem, where you wind up saying that the average potential of all the different particles is -2 times the average kinetic energy for a bound system. This is just minus gmm over r. This is 1/2 mv squared. The 2's wind up canceling, and you wind up getting the same answer. So it's the same sort of consideration that you might have. Just a silly cartoon depiction of what we've got here. If we're measuring the sun moving around the galactic center through this disk, this is this mass interior. And it matters not just what the mass is in the disk, but it actually matters what the whole mass is in the 3D distribution interior to our motion. And we'll get into a bit of the mathematics here in just a second. But this is the rotation curve that we should expect for the Milky Way. So here's a cartoon model of the Milky Way. Remember, it's a halo plus a disk. And if you say that there's sort of an equal distribution of stars or matter or whatever as a function of, sort of volumetric units, so per parsec cubed, and you just start coming up with a cartoon of what the rotation curve should be as a function of radius, you might expect, as you have some sort of spherical distribution, to increase very quickly. And then as you wind up running out of mass, because you're just in the disk and you only have a plane of material and not a 3D distribution of it, that you would wind up sort of having some characteristic fall off. If the mass is all concentrated centrally, that is, at r equals 0, then v as a function of radius is just going to be equal to the square root of gm over r. So it's just going like r to the minus 1/2 because m is fixed. That's what you see on the outskirts over there if we're essentially running out of mass because all we have are we're just adding a little bit from the disk. But this is also the rotation curve of the solar system. All the planets, as you might expect, wind up telling you that the mass of the sun is the same. Although, if you think about it, the mass interior to Jupiter's orbit is going to include the mass of the sun plus all the mass of the other planets interior to that. So it's actually going to wind up having a slightly higher velocity than you might expect just by taking the total mass of the sun. But this is almost imperceptible given that the mass of the solar system is almost completely dominated by the mass of the sun. So even adding Jupiter mass to that is only a small perturbation on what that rotation curve should look like. All right, so let's talk about how we actually make measurements of this rotation curve, because as we said, we can only make a measurement of the sun's motion around the center of the Milky Way. But we want to now see how the other stars are moving. And this is kind of a hard problem if you can imagine this, because you're moving and you're looking at stars that are at larger radii and smaller radii to you, and you're looking at how those are moving. But stars have their own sort of peculiar idea about which direction they should be moving relative to the sort of bulk flow of all the stuff that's sort of at the same radius, right? If the Milky Way was collapsing, you can imagine there's actually a radial component to how most of the stars are moving, right? That everything would be moving in, or if it was expanding, you can imagine all moving out. If it is sort of happily moving along basically in the form of a disk, and you don't basically assume very large elliptical orbits, which are not really favored because you have all these tidal effects, which wind up giving you circular orbits, then looking at the motion of stars at different radii and then sort of subtracting off your own known motion around the center of the galaxy is really the way that you make measurements of the rotation curve of the Milky Way. We're looking for bulk motion. That is, when we don't really care whether, star 132,347,000 over there happens to be moving in its own little happy, peculiar direction, right? We're looking for bulk motion, and a great view of bulk motion comes to us from the bulk motion of gas. How do we make measurements of the bulk motion of gas? How do we even infer the presence of, say, large amounts of hydrogen? 21 centimeter line. Remind us what that actually means.
So in hydrogen, there's the spin coupling, and there's two different states.
Mm-hmm.
And then when we flip states from the higher to the lower one, the atom releases a photon that we can see at 21 centimeters.
Okay, that's exactly right. So 21 centimeter emission is one way we could do this. And how would we get the rotation curve from 21 centimeter emission? How would we know how fast a cloud's moving towards us or away from us? Yeah, it's a very, very narrow line quantum mechanically, but we could see these lines actually shifted back and forth. And if we're looking at bulk motion of gas, there's going to be some broadening, a thermal broadening, because that one sort of gas blob has internal motions associated with it. But that tends to be much, much less than what you get from overall sort of effective thermal motions from individual stars, which could have much higher velocities. So if I could figure out a way of making a measurement of distance of a gas blob, and I measured its Doppler velocity relative to us, I get a measurement of the radial motion of that blob towards me or away from me. How would I make a measurement of the distance to that blob, right? Because it helps not at all to sort of find a blob but not know its distance, yet know its Doppler velocity very precisely. based on what we talked about last time. How do we make measurements of distance? Yeah, so it could be that we get lucky enough that this gas blob is close enough to us that we can make a measurement of the parallax of a star which is perhaps embedded in one of these gas clouds. If it's, remember, this H1, so capital I, this 21 centimeter emission from neutral hydrogen is fairly diffuse, and it's actually not that strong. Remember, you said we needed 10 to the 14 hydrogen atoms to get one of these 21 centimeter photons being emitted over the entire cloud per second. So if we're trying to make a very sort of strong measurement, we need very big clouds. Probably what's better is if we wanted to make a measurement, a very precise measurement to a distant cloud, we might want to focus on, say, molecular clouds, which themselves can be large, but they have sort of cold cores associated with them. So we're looking then at a very specific distance. What could we look for if we're looking for cold clouds? What's the types of emission or absorption that we might be looking for? Anyone remember? Yeah, CO. CO and actually other molecules are a good proxy of places where there's little cold clumps. And there you could imagine we're looking at a star-forming region, and we could find a few stars that we can measure parallax. But this is a very tedious problem, right? Instead, what people do in making measurements of the 21 centimeter emission for rotation curves is they use just a little bit of geometry to infer what the rotation curve is a function of radius. So bear with me for a second while I try to sort of draw a cartoon of the Milky Way, now in sort of concentric circles, which are meant to illustrate spiral arms or motion, circular motion, where we assume that the velocity along as a function of distance from the galactic center, we assume that that velocity at any one radius is going to wind up being the same. If it wasn't the same at a given radius, you can imagine you have a lot of bunching up, right? Because if this part over here was moving faster than this part over here, eventually it would wind up catching up. It would all glom together. But for the most part, you can assume this isn't exactly true in and around spiral arms, that it's basically the same velocity. So I'll draw 4 concentric circles. Now we're looking down onto the disk of the Milky Way. And I'm looking down on the disk of the Milky Way. We're going to live at one of these locations. Just put it at the bottom here on the 3rd circle. And now populate this Milky Way with lots of neutral hydrogen. Put it all over the place. There's gas blobs all over this place, right? We can look off in any direction. And remember, I showed you a full map of CO. You can also do this full map in neutral hydrogen, 21 centimeter. You can look at any B or L, right? Any angle off the plane or around the plane. By the way, we're looking again at B equals 0 towards the galactic center, L equals 0. If we wind up sort of defining some sort of angle here, and we call this angle L, then when I look at the galactic center and I move, say, 10 degrees off the plane, then I can look along a given line of sight. One of the nice things about hydrogen clouds is they're more or less transparent to emission, especially radio emission. And so if I have, say, a neutral hydrogen atom over here, which is radiating in 21 centimeter in its own frame, and we wind up observing it over here, it's passing through all these clouds. It could undergo some amount of absorption, except if all these clouds are moving at different velocities, then they're not going to be very happy absorbing a 21 centimeter photon, which is Doppler shifted away from where they quantum mechanically want to be doing that absorption. So if I emit in 21 centimeter, and I emit through a bunch of clouds that are all at different velocities, most of that stuff isn't going to get absorbed at all, but pass right through. So when I look along a sight line here, so I just point my radio dish and I point at some L and B, I wind up getting some emission from in what I infer to be 21 centimeter. And I can associate that emission. So here's some sort of flux. Here's some sort of wavelength. But if I don't want to do it in terms of wavelength, I want to do this in terms of velocity, right, which is going to be related to the delta lambda over lambda. What you wind up seeing is you wind up seeing a bunch of these different structures. And I'll tell you what all these velocities actually mean in just a minute. But each one of these sort of large bumps in the 21 centimeter line corresponds to a spiral arm. Okay, so let's look at sort of the geometry of how we're moving. For this purpose, what I'll say is that the sun is moving tangentially around its concentric circle, right? Is that right? Yeah, I haven't really. I didn't draw the tangent right, but yeah, it's going like that, right? Let's sort of zoom into that vector, and I'll sort of draw this line in the direction that we're going to wind up looking, and we've got our motion. We've got our motion L here, velocity v, and we're going to wind up projecting this velocity along this vector here. So our motion in the direction that we're actually pointing will be non-zero in general, right? And so there's just a projection, which is something that I can know just geometrically of how my velocity, even though I'm pointed in this direction, I have some sort of component of the velocity along some other random arbitrary direction. Each one of these parcels of gas, where I wind up intersecting along the line of sight, are all going to be moving in their own way. So each one of them are going to wind up having a projection along the line of sight, which, assuming that the velocity is almost constant or near constant for all these different concentric circles, which arm or which concentric circle do you think gives me the largest effective velocity away from me? What's that? The little one. Why is that? All of its motion is directly away from you. This little arm is on, by construction of how I drew these circles, the tangent point of this intersection. This radius here, something we call r min, and this distance that we have from the galactic center to where the sun is r0. So we've got an angle, we've got r0, we've got r min. We want to know the distance to that source. But what we really want to know is what the velocity is as a function of r min. What I've just done is we've come up with a nice construction of how we get r min and a velocity, because that velocity is entirely the circular velocity modulo the sort of a little amount that we have in that direction. And we can just subtract that off, and we can get an overall velocity. So typical numbers that you might see here, if I wind up labeling this as arm A, arm B, arm C, arm D, is that this would be A, this would be D, and our zero velocity might be at C, where we are. This might be about 100 kilometers a second away from us. This might be, say, minus 50 kilometers a second towards us. Because if we think about this, the velocity projection in this direction here may actually be, in this direction here, may actually be less than our overall velocity projected onto this direction. So just from the geometry of it, d equals r cosine L. Obviously, L is in units of radians at the velocity of max, V max is right here for spiral arm A. And likewise, R min divided by R0 is equal to tan L. So that we can use this to measure V as a function of R min, which is basically just measuring the rotation curve. So the obvious thing here is that 21 centimeter emission obviously reveals spiral arm structure. As does, by the way, CO measurements. We can see the spiral arms in that. And it gives us a dynamical measure of the Milky Way mass. Now, not just at where the sun is with respect to the galactic center, but at all radii. So what does that actually look like? Well, maybe not what you expect. This is a sort of depiction, although obviously not showing errors on the data and things like that, of what our so-called rotation curve looks like within the Milky Way, using 21 centimeter emission and similar means. What you see is that at 0 distance from the galactic center and moving outwards, we wind up seeing a very rapid rise from a small velocity to a large velocity. I'll talk about that in just a minute. And then it sort of falls off, and it looks like it's going to fall into this 1 over r to the 1/2 power. But it doesn't. It actually picks back up. And then it sort of wobbles around and keeps on going. And out to something like 25, 30, maybe even 40 kiloparsecs, it appears to be what we call flat. It's not exactly flat, but it's clearly not going all the way down like this, right? So it's telling us that as we go to larger and larger radii, the mass interior isn't actually sort of fixed, but is growing as I get to larger and larger radii. Well, you don't have to see that. I mean, so what does this actually mean if we think about this in terms of velocity vectors? In the solar system, this is basically a depiction of what I already showed you. The solar system, you see this rotation curve right here. And you wind up obviously having the mass interior being basically the same as what Uranus sees and what Earth sees. And the closer in we are to this central mass, the larger the velocity vector. But what this is saying about the rotation curve is that all of the different parcels of gas and stars as a function of radius, once I get out of sort of 2 kiloparsec level, they're all moving at about the same velocity around the sun. What if we thought of the Milky Way as a disk, and I mean like a disk, like a CD disk, or I don't know, Blu-ray disc? Is that what you guys use? You don't even use discs anymore. People used to talk about this in terms of record. Solid body motion. So I had some sort of solid structure. How would velocity increase as I get to larger radii? If I had the same angular, right, if I have the same angular speed around, right, so it means that if I'm at a very large distance, I have to cover a much larger circumference than I would if I'm at a smaller distance. You'd imagine that the velocity is going to wind up increasing with r. So there's some sort of solid body rotation, that everything's sort of moving together, but the things that are on the outskirts have to move faster just to keep up with the stuff on the inner part. We see none of that in the two sort of dynamical systems that we know very well. All right, so let's sort of think a little bit about the physics now of how we might give rise to this very interesting rotation curve. First of all, I'll draw it out for you so you have it in your notes, and then we'll sort of parse it and try to see what it means for the mass interior, because that's really the thing that we're interested in. So I'll carry this out to 30 kiloparsecs from the center. This is R, and V orbital, 100, 200, 300. In the central regions, it looks like we get up to something like 250, and this goes with V of R, so about proportional. This looks a little bit like solid body rotation in the inner 2 parsecs. Then it comes back down and sort of wiggles around like this and keeps on going as far as we know. Should have dropped down like this. This would have been in the 1 over square root of R. Not seen. This would have been if all the mass was concentrated near the center. And you already know that this sort of typical number here is something like 220 kilometers a second. And we know that this is what we call a flat rotation curve. So certainly by 10 kiloparsecs, this should be KPC. By 10 kiloparsecs, we're sort of well inside the, this flat rotation curve. All right, so let's go back to this mass interior to some certain radius, v squared r divided by g. If we look at this functional form for understanding what the mass is internal to some radius, what do I get out of this if I look at a flat rotation curve? That is, what does a flat rotation curve mean for the terms here? G is a constant, so it's either going to be with v or r. What does a flat rotation curve mean? As a function of radius, v is constant. It's about constant. So this is going to be some sort of constant, whatever it is, times r. That means that the mass interior to some radius as a function of r, or the mass enclosed, is just going up and up and up, out to 30 kiloparsecs and beyond. So what do we say about the distribution of stars as a function of radius? What's happening as I get to larger radii? It drops off exponentially. So we already have this idea that it very likely isn't stars that's giving us more and more mass, right? As I get to a larger radius, I see more mass interior. If I get to a larger radius, I see more mass interior. By the time I get to 30 kiloparsecs, there are very few stars out there that are dynamically associated with the Milky Way. And yet there's H1 gas that we can observe. And we can actually see that that gas is moving very rapidly, as if there's more mass between 8 kiloparsecs and 30 kiloparsecs that we don't have a way of seeing. So matter interior increases to the largest distances of the Milky Way. And it appears that there's even more matter beyond where the visible stars are. The fundamental question of this dark matter stuff is, what is its distribution? Can I erase this word? Yeah. What is the distribution of dark matter in the Milky Way? A natural place that you might think that this dark matter stuff might reside would be in the plane of the Milky Way, right? Because that's where most of the stars are, that's where most of the gas is. A big question is that actually true? So a way in which we can get at that question is by looking at the sun's motion above and below the plane. We can actually look at the velocity of motion of the sun as it actually oscillates above and below the plane of the Milky Way. We're currently a bit above it, or if you turn yourself upside down, we're below it. But we're not exactly in the plane of the Milky Way, and we actually have a small velocity, about 7 kilometers a second, we believe, moving out of the plane. We can also look at a bunch of the stars around us and ask what their sort of average velocities are. And we can come up with an overall sense of the typical velocities of stellar motion above and below the galactic plane, which is also a way of us making a measurement of the sort of accelerations that these point particles effectively wind up feeling. So to sort of get ourselves situated on this, what we're going to wind up doing is figuring out what the matter density or mass density is of stuff inside of the galactic plane. And then we're going to wind up thinking about whether that's actually enough to account for this dark matter. So is it in the disk? That's the question. And because we can't see it, the only thing we can do is try to understand its gravitational influence on our motion, right? So let's try to figure out what effectively the gravitational attraction is towards the disk. It's actually fairly helpful if we think about the disk of the Milky Way, because we want to sort of come up with some basic numbers of what that gravitational attraction actually is, and overall what the mass density is inside of the disk, is to consider the disk basically an infinite plane. This allows us to do some sort of electrostatics type of thing where we use Gauss's law. Yeah. It's not exactly right, of course. The disk is falling off. But what you wind up noticing, of course, is if the sun is above the disk and it's feeling this gravitational attraction back towards the disk itself, it's going to feel an acceleration down towards it. You can imagine that for particles or other stars or other gas parcels that are far out, we're not feeling that much of an attraction because of that stuff that's really far out. It's the stuff that's sort of nearby. The way that we go about this, so let me just sort of orient ourselves with a bunch of vectors. Remember, in cylindrical coordinates, when we think about the galaxy, the location above the disk midplane is symbolized with this z. And if we're sort of above here at some distance, we're going to feel a gravitational attraction back towards the disk midplane. G is just going to be G capital M, what I'll call z hat, so it's in the direction of z r squared. And we have to understand which direction we're actually looking. In this case, it's going to wind up being pointed downwards. From Gauss's law, does anyone remember what Gauss's law is? Gauss's law tells us about electrostatics. That's right. So the flux in electrostatics, the electromagnetic flux outside of some parcel, regardless of what it is going to be defined by the stuff interior to it. So that means that I can look at the area around some collection of charge, and I can figure out what the total charge is around there by looking at the flux, right? Without having to know the precise distribution of charge interior to whatever volume I wind up creating. There's a similar sort of concept using Gauss's law in the context of gravity, where if I draw some arbitrary volume around some arbitrary mass, all I have to look at are the force field lines at the surface on that volume, and I can wind up inferring what the total mass is interior. Yes?
You're bringing up this electrostatic force. words, we observe the Milky Way moving in this strange velocity pattern. And why do we assume that there's a missing mass, missing gravity? Why don't we just, or has anybody considered that there's a missing force?
Sure, yes, that's a very important question. I used the more or less Newtonian derivation of what mass is interior. We'll use Gauss's law to figure out mass interior for a plane now, but instead of a point source, you could also use Gauss's law. All of that stuff is predicated on a 1 over r squared law. That's why it works with. That's why it winds up working with electrostatics. If the 1 over r squared law for the force of attraction between two pieces of mass is not right on large scales, then I have tricked us into believing that what's missing is actually mass, right? Because the motions that particles might decide to take might be actually modified by some sort of other force. Typically what people think about, because the 1 over squared law works really well in the solar system, right? I mean, that's been tested very accurately. It works really well on short scales. In fact, people are looking for sort of multiple dimensions beyond the 3 spatial dimensions by looking at the departure of the 1 over r squared law at sort of the millimeter scale now. It's thought that these other dimensions are actually, I'm sorry, I'm going off on a tangent, but these other dimensions are actually small relative to our large 3 dimensions, so that you wind up sort of seeing the departure in our 3 dimensions of the 1 over r squared law in really small distances. So people are trying to test this in the lab. And there's certainly a Nobel Prize or two in that if they see it. If they don't see it, then they're just going to be great physicists that didn't hit a home run. But it's natural to think about how the 1 over r squared law might also be changed. This, in general terms, is called modified gravity. And people have for a long time you can come up with what that extra term has to be in the 1 over r squared law to give you a flat rotation curve. The problem is then it starts breaking down in other places where if that's true, then you wind up having to have the assembly of mass over the lifetime of the universe assemble in a different way and things like this. And we can see actually, we can actually test within the solar system using every planet as a point particle of how well that 1 over r squared law works and what the constraints might be on these sort of modified systems. So only very recently have people come up with a relativistic or general relativistic version of modified gravity. And it's jury's not yet out on how wrong that is, but most people believe that that's actually wrong and testably wrong. But certainly there are people who are thinking maybe just GR is wrong on large scales. But it's a good insight, and all of this is predicated on the idea that 1 over r squared law is right. Is there another question? Okay, so Gauss's law in the context of gravity will say that for any closed surface, if I integrate the quantity g vector times the area vector on that surface, I wind up getting minus 4 pi g times the mass enclosed. You can convince yourself that gives you the 1 over r squared law if you just have a single point mass in there and you just draw a sphere around that point mass. All right, so let's actually draw a volume that allows us to get some traction on this. And what we'll do is draw some sort of spherical tube above and below the plane, with the sun at the top of this right here. So this is now trying to figure out what the mass interior to us is. If all the mass is now in this plane, then this is our way, by measuring the acceleration, of figuring out how much of that mass is actually there in the plane. And what we can do, I said the sort of g direction is pointing downward here. The little differential area is pointing out in this direction here. And likewise, when I'm down here, I have some other little differential area pointing in the opposite direction. And which, if I'm down below the plane, how am I being pulled towards or away from the plane? Up or down? Up. Right. So what you can see here is that you've got two quantities right here, and they're actually parallel to each other or anti-parallel to each other. So I have a non-zero answer for these surfaces here. What about this surface in the cylinder part, the long part? Y0? Well, what's the area vector looking like for that parcel of the shape? Outward, yeah. So everywhere the area is pointing outward. But gravity is pointing up or down depending on where I am on this long tube. So all the contributions from everything on this long tube go to 0. So all I really have to consider is that I have G and some sort of area. And you can see that I wind up having contributions of negative because these things are anti-parallel with each other. And these vectors here are also anti-parallel. So I'm going to have, and they're the same. So I'm going to wind up having minus 2 times the vector quantity of G times A. This is equal to minus 4 pi G M enclosed. This says that the strength of gravity, the acceleration that I wind up feeling, is just going to be 2 pi G times mass enclosed divided by the total area. And this is just 2 pi G sigma, where sigma is called the mass density or mass surface density. And this might be in units of, say, solar masses per parsec squared. Right, it's the integrated mass. So if I had some distribution of mass in 3 dimensions, I integrate in this dimension here, and I wind up getting this sigma right here. It's a little bit like column density when we think about a collection of particles and you integrate along one of the directions, right? Well, what's interesting about this is that G is independent of Z. Right? And this is a sort of strange thing that you've probably seen in your electrostatics class, where you have some infinite charge sheet, and then you have some oppositely charged particle, and no matter where it is above or below that sheet, it feels the same force back towards that sheet. So it's effectively the same thing that's happening here. The sun oscillates above and below the plane with a period of 85 million years. So for every sort of full orbit that it winds up taking, remember that took something of order 500 million years. For every full orbit that it takes, it's going up and down and oscillating above and below the plane. And it's a constant force downward, so it's really like almost like a spring, right? It's just going up and down below. It's not actually getting damped out. Over a very long time, that's going to wind up not being true, because eventually the sun is going to wind up accreting enough of the interstellar medium that its mass is going to increase. That's going to act a little bit like a drag on the whole system. And so we're going to eventually wind up damping down. The sun VZ, as I said, is about 7.2 kilometers a second, currently moving above the plane. And likewise, we can look at its acceleration and figure out what the mass is interior. If the mass was concentrated in a disk, the velocities relative to the plane would be higher, as I said, and likewise the accelerations. And this is just not observed. So our conclusion from this little exercise is that dark matter is not concentrated in the disk. And instead, what we say is that it's not concentrated in 2 dimensions, but basically distributed over 3 dimensions. We say that there is a dark matter halo. And it has a very large extent. I didn't actually give you the numbers of what we'd expect for different amounts of dark matter, but this number is incredibly low relative to what it would be if you put all the dark matter in the disk to account for the flat rotation curve. So if it was all there, we'd have a huge acceleration above and below. Everyone would be feeling this really strong up and down, right? But we don't have that at all. It's sort of this sort of gentle up and down. And so probably most of the mass, in fact, we know most of the mass that's in the disk is just in the form of stars and gas. And you can actually do that sort of accounting and figure out that our acceleration and our velocities are consistent with that hypothesis. Let's look at the density of the dark matter halo. And we consider this as a mass density as a function of radius, mass per unit volume, in some local volume at distance r from the center of the galaxy. And consider a mass in a shell at some radius with mass dm. So that means that our density is just going to be dm divided by 4 pi r cubed dr. That's the volume of the shell. And the differential volume of the shell, that's the differential mass. And so this is 1 over 4 pi r squared dm dr. This means that if I have a clever way of figuring out what dm dr is, I can infer what the density is of this dark matter halo is as a function of r. We spent the first half of the lecture talking about our clever way of figuring out dm dr. We know what the mass enclosed is. So I can actually do integrals here and figure this out. V squared is equal to gm less than r divided by r. That's just from what we had before. So if I sort of put an r onto the other side, divide by g, I wind up solving for m. I can then take the derivative of that with respect to r. So m less than r is equal to v squared r divided by g. I take the derivative of this with respect to r. What is that? V squared over g. I can just plug that back up in here, and I get v squared over g times 4 pi r squared. So, if the density of the dark matter halo followed this distribution, as in it fell off as 1 over r squared, given that I have a flat rotation curve, then I would exactly account for that flat rotation curve. In fact, this works for any velocity profile that I wind up having, but because this is flat, then I don't have to worry with all the different integrals because this is not as a function of r. Since v is constant, or approximately constant, that means that the density of the dark matter halo is going like 1 over r squared. Remember, what's the density of stars doing as a function of r? How's that changing? No. No. Exponentially. It's going down really fast, whereas the dark matter halo is not going down really fast. Dark matter halo extends out to very large distances. What's that? We measure it to be. If it wasn't, we'd have a different inference about that, right? And in fact, if v is decreasing very rapidly, if you did the integrals outright, you'd find that you don't need a dark matter halo, because all the mass would be concentrated in one place. Okay, so this is pretty neat. We've inferred something using rotation curves about the distribution of dark matter in the Milky Way. That's something. I think that'll be the coolest thing you learned today, but that's just me. What's wrong with this, though, if we think about this sort of mathematical definition of this dark matter halo at large and small radii? What's wrong at r equals 0? What's that? I think people are saying, why didn't you say it? Infinitely dense. Infinity. So that's clearly wrong. Yeah, but that black hole is a finite mass. It turns out that this is okay on sort of scales outside of the gravitational influence of the black hole. Inside of that, the black hole is accreting dark matter. What about large distances? That's not so obvious. Well, let's just write it down. So r approaching 0, this blows up. So that's not good. R approaching infinity, what's wrong with that? Yeah, that's not wrong.
It doesn't go to 0 fast enough, does it? Because it has to stop at the edge of the galaxy.
What's the edge of the galaxy?
R.
Big R, the magical big R. A billion light years. What's the mass of the Milky Way? How would I actually determine the mass of the Milky Way if I basically say, forget about all the stars and gas, let's just think about the dark matter? The total mass of the Milky Way is just the integral from 0 to r, in this case infinity, of 4 pi r squared rho dr. That also goes to infinity. Right, because these two r squares wind up canceling out. I have a finite number here, but I have an infinite number there. So at large scales, this also has to be wrong. So let's look on the short scale first, and then we'll think about this large scale in a second. And I'll tell you that this parameterization of the dark matter halo isn't exactly right. We have a different functional form that we wind up using. As I said, within r less than about 2 kiloparsecs, we saw a different functional form that v goes something like r. That's actually as observed. So what does that mean for the density interior and for small radii? So less than 2 kiloparsecs from the center of the galaxy. V goes like r. So v squared goes like r squared. R squared cancels r squared, and we have a constant. So if I have sort of a uniform density of material as a function of radius from the center of the Milky Way, and I wind up integrating that, I wind up getting a rotation curve that looks like solid body rotation. So the way that we actually parameterize the dark matter halo is we say that the density as a function of r is some sort of constant, which is called C0, divided by some constant a squared r squared. And you can see that the behavior is actually kind of nice here, and this is true for r less than about 250 kiloparsecs. Just give you some of the numbers. C0 is measured to give us the rotation curve, 5 times 10 to the 8 solar masses per kiloparsec. That's the units. And A is about 2.8 kiloparsecs. All right, let's look at what happens on these different scales that we were worried about with the parameterization that I gave you there. On small scales, what happens? When r goes to 0, rho of r starts going to what? Yeah, C0 divided by a squared. When r is infinity, that still goes to 0. But if I truncate, so I actually say the dark matter halo sort of cuts off at some radius. Well, it's going like 1 over r squared. I still have that problem at infinity, but of course, as I think someone already mentioned, the galaxy is not infinite in extent. It actually lives in a grouping of other galaxies. So our dark matter halo is very likely overlapping the dark matter halo of another galaxy. Here's a depiction to give you size, sort of an overall size sense of the dark matter halo relative to the stars. Luminous stuff just occupies a tiny amount of what you think about as the gravitational influence of the Milky Way. It's completely dominated by this dark matter stuff, and it goes out to very, very large scales. And you might think, well, we've made our measurement of the rotation curve incorrect, and so therefore, we're sort of bamboozled into believing that there's this dark matter stuff that isn't there, and it has this special distribution. But it turns out that when we make rotation curve measurements of other galaxies, so nearby galaxies, these are spiral galaxies very much like our own, that happen to be edge-on, and we can make a measurement of the velocity of each sort of parcel of gas or stars moving towards us or away from us, you wind up noticing that they also have flat rotation curves. And they have curves that look very, very similar to the Milky Way. This appears to be a very universal distribution of how dark matter is distributed around galaxies. And if you want to think about what's important as galaxies wind up assembling themselves, as we'll see from smaller galaxies over the long history of the universe, what matters the most is the distribution of dark matter. The stars and the gas just sort of are kind of indicators or lighthouses of where most of the important stuff is. Which one of these galaxies has the largest mass? The black one, why? Yeah, so the rotation curve is the largest. That actually has the largest velocity. That has the largest mass. And likewise, the one that has the smallest is down here. The galaxy that's most like our own has a flat rotation curve. These two are sort of very similar to our own Milky Way. So when you see spiral galaxies and you see these things edge on, and even if they're not edge on, they're sort of inclined with respect to you. If you can measure the inclination angle of how the disk of that galaxy is with respect to you, and then you can back out what it would look like if it was edge on, you get a perfect measurement of the velocity of stuff moving towards you or away from you. And it appears to be more or less a universal profile of how the gas and the stars move in spiral galaxies. So just to end with a couple of numbers, locally, that is at 8 kiloparsecs from the galactic center, these are things that we can actually measure. The density of stars is 0.05 solar masses per parsec cubed. The density of the dark stuff in sort of the region that we occupy within the plane is something like 0.01 solar masses per parsec cubed. So they're actually comparable to each other. And we can't measure the density of the dark matter stuff directly, right? That's actually what we'll see and we'll talk about next time, is how we can actually infer what this stuff actually is. And what you'll see is that while some of this work is happening here at Berkeley in laboratories to try to understand what dark matter is, a large amount of the work is happening on astronomical scales. Like general relativity, most of the most interesting tests of general relativity are happening because astronomers are around and we're awesome. So this is something that we want to understand. is that distribution, and in particular how we get so much dark matter around us, how it has the distribution that it does. But in just sort of understanding this infinity here at large radii, I think it should be clear that if we have the Milky Way and its dark matter halo, it's effectively overlapping the dark matter halo of Andromeda. And many of the satellites around us, all the little galaxies, have their own sort of dark matter halos that they're associated with. But the sort of dominant mass that is seen by any point particle within the local group of galaxies is the two dark matter halos of the Milky Way and Andromeda. All right, so I'll end with that. We'll talk on Thursday about the nature of dark matter. Then we'll start talking about rotation curves of other galaxies. And that sort of is our segue into understanding the different types of other galaxies there are in the universe. I have my office hours at 3:30 today. And remember, by the end of the day today, we will post the somewhat longer problem set of 6 and 7.